Welcome back. So, now we continue to a new topic. We have discussed earlier that in the case of American call and a non-dividend paying stock, a call is on a non-dividend paying stock, it is never optimal to early exercise the American call. I repeat, if you have a stock and on the stock you've got a call option, you bought a call option on that, and the stock is a non-dividend paying stock, that's a very fundamental condition under which this theorem operates. Then it is never optimal that the option should be exercised early. Remember, it's an American option, so it can be exercised earlier, but by virtue of arguments we establish that it is not optimal to exercise the option early. Let us see what happens in the case of a dividend paying stock. In other words, what we are going to investigate now is the case of American call, which is on a stock which is paying dividend. For simplicity, we will assume that there is only one dividend payment during the life of the call option, and we examine in what context or what are the conditions under which it would be optimal or otherwise to exercise the American call. First thing that we need to establish before we get into the nitty-gritty is that if the stock is going to pay dividend within an interval, say 0 and capital T, this is the life of the option and it can be exercised any point within this. Let us say the expected dividend date is T d, that is somewhere between 0 and capital T. Now, we need to establish that we need to investigate only the situation where the stock or where the call is exercised at T d. In other words, it is sufficient for us to investigate this particular aspect, this particular question at the point T d just before the stock goes ex dividend. What I mean is, it is not necessary for us to examine the viability of this proposition at an earlier date prior to the dividend going prior to the stock going ex dividend date. Why is that? Let us first answer this question. Now, if the stock were if the call were to be exercised at an earlier date, let us say somewhere around here at T, and I would hold the stock until the ex dividend date, I would get the stock and I would also get the dividend, that is fine, but I would make the payment at the point small t. However, I could generate the same portfolio of the stock and get the dividend also by exercising the call just before the stock goes ex dividend, and I would also have saved on the amount of interest that I would have incurred on the payment of the stock price for the period between small t and T d. That is one thing, similar to the argument we gave in the context of the non-dividend paying scenario. But one thing is that I save that amount of interest, and the second thing is of course that if the stock price was going to go down, I could retract my decision of exercising the call and getting the stock. So, in this situation again it would be appropriate to exercise the option at the ex dividend date or just before the stock goes ex dividend, rather than far earlier than that or rather than earlier than that. So, that argument is parallel to the argument that we gave in the context of American call on a non-dividend paying stock. So, what we need to investigate therefore is the situation where we are examining the two options. Number one, exercising the American call just before the stock goes ex dividend and not exercising the American call. These are the two options that we need to examine. Now, suppose I exercise the American call. If I exercise the American call, I will get this amount of payoff, whatever is the stock price as on the dividend date, date on which the stock goes ex dividend, STD minus whatever I have to pay, the exercise price. So, this is my payoff under the option if I exercise the option just before the stock goes ex dividend. Suppose I do not exercise the option, then what happens? If I do not exercise the option, as soon as the stock goes ex dividend, the stock price will fall. The stock price will fall by the amount of dividend. Therefore, the new stock price immediately after the stock goes ex dividend is STD minus D. This is the ex dividend price, STD minus D. This is the price that would be available after the ex dividend date. Now, if with this price in the market, what would be the lower bound of the call? The lower bound of the call, we talked about this earlier. The lower bound of the call is given by S naught minus K e to the power minus R t. Adapting this formula to the current scenario, I get the lower bound of the call is S T D minus D, which is S naught for today after the stock goes ex dividend. This is the current market price, minus K e to the power minus R T minus T D, which is the remaining time to maturity, of the call. So, in other words, what I am trying to say is that if I exercise the call, I would get this amount of money as T D minus K, and if I do not exercise the call, my call would be worth at least within inverted commas emphasized, at least this amount of money. So, if this amount of money is greater than my payoff from exercising the call, then obviously, you see, the point is this is a lower bound. So, the value of the call could well be more than this, the value of the unexercised call could well be more than this, but at least it would be this. So, that being the case, if this amount of money is greater than my payoff, then I am surely not justified, it is not optimal to exercise the American call before the stock goes ex dividend. You should rather retain the call unexercised. So, D is less than this quantity, then it is surely not optimal to exercise the call, you should not do it. So, D is less than this, then it is not optimal to exercise the call. However, what happens if D is greater than this? Now, if D is greater than this, the above analysis does not conclusively establish that it is optimal to exercise the call option. It does not conclusively establish. However, for any reasonable assumption about the underlying stochastic process of the stock of the underlying asset, it can be shown that if the stock price STD is sufficiently large, then this condition would be satisfied, and hence it would be optimal to exercise the call option. So, what do we have? Let us recapitulate. If this expression, this is the value of the call, this is the lowest value of the call, the lower bound. If this lower bound is greater than this, then it is surely not optimal that you should exercise the call option. This translates to this, that D is less than this. In other words, if the dividend is less than this expression, you should not exercise the call option. If D is greater than this expression, then this analysis that we have done does not conclusively establish that it is optimal to exercise this call. However, based on a reasonable assumption of this stochastic process to be followed or being followed by the underlying asset, if this condition is satisfied, then we can say that it would be optimal to early exercise the American call for sufficiently high values of this expression. So, what have we concluded? We have concluded that if there is no dividend, if this stock is not paying dividend, then it is certainly not optimal, because this would be 0, D is 0, and this condition would invariably be met. So, if D is 0, then it is surely not optimal to exercise the call early, which we have already established by other grounds. So, this is consistent in that sense, but if the dividend is large enough and this period is small, in other words, the payment of dividend is pretty close to the maturity of the call, then there could be a possibility, there could be a strong situation, there could be strong justification in exercising the call before dividend. So, that is what it is. Now, we come to another interesting result. The interesting result is called Girsanov's theorem. What Girsanov's theorem says, although it is a very technical theorem, we shall talk about, we shall leave out the mathematical nuances, we shall talk about the philosophy of the theorem and in context of our pricing. What it says is that, see, we have been talking about real life probabilities, we have been talking about risk neutral probabilities. So, it is interesting to explore the interrelationship between them, and Girsanov's theorem gives us that interrelationship. The interrelationship says that when we move from one world to the other, that is when we move from the real world to the risk neutral world or vice versa, the expected return changes, the drift changes. However, the volatility remains unchanged. The volatility, the underlying volatility, if you move from the risk neutral world to the real world or vice versa, remains unaffected. Of course, the rates of return and the trends or the drifts terms do undergo a change. Let us see the background behind this using this single step binomial model. This is the simplest exposition of this theorem, but this serves our purpose. Consider a single step binomial tree of length delta t, you can take any length in the risk neutral world. The important thing is that it is a single step binomial tree. So, the stock can either go up to US0 or it can go down to DS0, that is the only thing. It is S0 here, it goes up to US0 or it goes down to DS0. That is what the single step binomial tree is, and this interval is delta t. Right. So, the expected stock price S of delta t, that is the value of the stock at this expected value of the stock at this point at delta t is q S0 u plus 1 minus q S0 d, standard notation. So, because we are in the risk neutral world, the stock will generate risk free return. As we have discussed, the stock must generate only the risk free return, or in the risk neutral world we only have the risk free return. And therefore, we must have S delta t is equal to S0 e to the power r delta t, and this equating this S0 e to the power r delta t as equal to this quantity, we get q is equal to this. Now, let us look at the variance. The variance of return, variance of stock return, that is important. Now, the return is given by S delta t minus S0 divided by S0, the change in price divided by the initial price. So, variance of this expression S delta t minus S0 upon S0 is equal to, because 1 again does not contribute to the variance, therefore, we have variance S delta t upon S0 is equal to E of this thing minus E of this thing. We are trying to work out the variance over a period delta t. So, defining sigma as the stock price volatility. So, sigma square delta t is the variance, right. Sigma square, therefore, sigma square delta t must be equal to this expression. Sigma, you see, we have included delta t here. So, we are talking about the change in price over time delta t, not per unit time. So, therefore, this expression is equal to sigma square delta t, and simplifying this expression is equal to this q into u square for this, and we are taking expected values. So, q comes here 1 minus q into this is for this, and this we have already done in the previous slide. S t is equal to S0 q. So, S t upon S0 is equal to this expression. If we substitute the value of q, in this expression, in this whole expression, and simplify, what do we get? We get e to the power r delta t into u plus t minus u d minus e into 2 r delta t is equal to sigma square delta t. Now, if you ignore higher terms in delta t, a possible solution, one possible solution, and this is due to Cox and Rubinstein. One possible solution of this is u is equal to e to the power sigma root delta t, d is equal to e to the power minus sigma root delta t. This can be verified here. U d is obviously equal to 1, so there is no problem. U plus t, you are expanding up to second order in sigma square, first order in delta t. So, u is equal to e to the power sigma delta t using the standard exponential for the expansion for the exponential function, we get this, and for e minus delta t we get this expression. So, the sum of these two turns out to be 2 plus sigma square delta t. So, e to the power r delta t into u plus t minus u d minus this expression. If you simplify this, you get sigma square delta t plus order of delta t square, which we ignore. So, this is what we get. So, up to order delta t, this equation is satisfied with these inputs. Now, in fact, we can conclude from here from this earlier this expression also for u and d, but if you like, you can also work out the same expression for the real world using real world probabilities, and what we end up with is basically that this expression for u and d, they are independent of r or mu in the case of real world probabilities, or r in the case of the risk free world. Here is the real world probabilities and p is the real world probability, q is the risk free probability. But in either case, we find that the same u and d satisfy the requisite equations. What does it mean? It means that although the drift rate is changing, here it is mu, in the earlier case risk neutral world, obviously it was the risk free rate, here it is the expected return on the stock, the risky return, but u and d do not change, the jumps do not change, and that means what? That is it is a very significant result, in the sense that because of this we can infer that when you move from one state of the world to another state of the world, your return, your drift changes, your expected return changes, but the volatility, the fluctuations do not change. This is a very important result which would be used even in later cases. This is called Girsanov's theorem. So, in a sense, what does it say? When we move from a world with one set of risk preferences to a world with another set of risk preferences, the expected growth rate and variable change, but the volatilities remain the same. This is the formal description of Girsanov's theorem at our level. Of course, I repeat, it is a highly technical theorem, and it involves a lot of mathematical nuances which we have overlooked in this interpretation. Now, we come to the Black-Scholes model. We have talked about the discrete version of option pricing. We have talked about using a discrete random walk, time in discrete steps, time in discontinuous jumps, price in discontinuous jumps. Both the time and the stochastic variable were taken as discontinuous. We relax both these assumptions now. We move from the discontinuous world or the discrete world to the continuous world, where time is also continuous and the stock price also has a continuous spectrum. So, let us quickly go through the assumptions. The assumptions are: number 1, the stock price follows a log normal process with constant mean return and volatility. Just a reminder, the stock price is given by log of ST is normally distributed with a mean of log S0 plus mu minus 1 by 2 sigma square t and a variance of sigma square t. This is in the real world. In the risk neutral world, what will happen? This mu will change to r, volatility will remain unchanged, as we just discussed in the context of Girsanov's theorem. Therefore, volatility remains unchanged, the expected return changes from mu to r when we move from the real world to the risk neutral world, then distribution remains the same. The short selling of securities with full use of the proceeds is allowed. Short selling means you can borrow the asset and sell it in the market in anticipation of a price decline. So, when the price falls, you can buy the asset and replenish it to the original owner. There are no transaction costs or taxes, that means there is no friction in the market. The markets are efficient, so that there is no distortion created due to taxes. Very often it happens that the capital gains tax is slightly different from the regular tax rates on other incomes, and as a result of it, this creates a distortion between our dividend income and our income arising from the appreciation and value of the stock or of other financial assets. So, we are assuming away these distortions. There are no dividends during the life of the derivative. This is another fundamental assumptions. There are no, and remember, we are going to value European derivatives. We are at the moment not concerned with the valuation of American derivatives. We are going to confine ourselves to the valuation of European derivatives. There is no riskless arbitrage opportunities. In other words, we are assuming what you call an efficient market, so that arbitrage will neutralize any price differences which are arising without any equivalent risk, or any risk differences. If there are price differences without any risk differences, they would be arbitraged away. Then security trading is continuous, that is an assumption that I just talked about. The risk free rate is constant and is the same for all maturities, that is another assumption that goes into this model. Black-Scholes model in fact is one of the most celebrated models in finance. After Markowitz and Sharpe, this is probably the most well known model in finance literature and in finance fraternity as such, investor fraternity as well. It has become very popular now, and we have Black-Scholes programmed calculators as well. So, this is very fundamental to finance. It's one of the cornerstones of contemporary finance valuation in terms of for contingent claims. So, let us now get to the valuation proper. We assume that C represents a derivative asset. C is a function of the underlying asset that we epitomize by S, and is also an explicit function of time t. So, C is a combination of S and t, where S is a stochastic variable, a stochastic process which is modeled at the infinitesimal level by the Langevin equation ds is equal to mu s dt plus sigma s dw. Obviously, dw is the standard Brownian motion and is equal to z root dt. Ito's lemma also we have talked about. Ito's lemma is given by this expression. The important thing is in the Newtonian framework, this term was missing, this term was not there, and this term came about. Why? Because the variance of this expression is not equal to 0. This is equal to dt, and that manifests it is not equal to 0, it is equal to dt. It is neither stochastic, it is deterministic, and as a result of it, the dt comes here with the second derivative. dw square goes with the second derivative, it is equal to dt without any stochasticity, and therefore, it is present here. And therefore, dg is equal to this expression, and this is the stochastic term. So, x is the stochastic variable, g is a function of the stochastic variable and t. Very now, note the similarity, that is important. G is a function of a stochastic variable which is given by this, and explicit function of time. G you can write as g is a function of g comma x comma t. So, g is a function of x and t, and just like c is a function of s and t, s follows this Langevin equation, this, and similarly x follows this equation. So, there is a 1-to-1 relationship. A and B are defined accordingly. A is defined as mu of s. If you compare these two equations, let us call it equation this and let us call it this. So, if you compare these two equations, you get A is equal to mu into s and you get B is equal to sigma into s. So, substituting these values in this Ito's lemma, what do I get? I get dc is equal to mu into s into delta c by delta s plus delta c by delta s t. This is the explicit time dependence, this is the explicit time dependence plus 1 by 2 sigma square s square del 2 c by del s square into dt plus sigma s del c by del s dw. Now, I construct a portfolio pi, capital pi, and that portfolio consists of, remember at the beginning of today's talk, I introduced this concept. We can construct a riskless portfolio consisting of a derivative and a position, a counter position in the underlying asset. That is precisely what we are going to do. We construct one unit of the portfolio pi, which comprises of one unit of the derivative and minus. What does minus represent? Minus represents as a position would be opposite to the position of the derivative. If the derivative is long, the stock would be short, and if the derivative is short, the stock would be long. They would be in opposite directions. Delta c by delta s units of the stock. This is in fact given a name, this is given as capital delta. Delta c by delta s units of the stock. So, the value of this portfolio at inception, what will be the value of this portfolio at inception? It consists of one unit of the derivative. So, it will cost me c, this will cost me c, and delta units of the stock. So, it will cost me delta into s. Delta is equal to delta c upon delta. So, this is and please note the negative sign because the positions are opposite. The change in the value of pi, change in the value of the portfolio pi due to a small change ds in time dt will be given by d pi is equal to dc minus delta c by delta s into ds. Now, there is a very important assumption embedded here. The assumption embedded here is that over this interval dt, what we are talking about, this expression does not change. In other words, the portfolio composition does not change, because this, you see, if this figure changes, the portfolio, what are we implying? We are implying that the portfolio composition changes, because the portfolio has been defined that way. The portfolio has been defined in terms of 1 and delta c by delta s. So, if delta c by delta s the slope changes, then the portfolio composition will also change. But for the moment, we are assuming that the time period is so small that this particular delta or this derivative remains constant over this small period of time, and therefore, d pi is given by this expression. Now, it can be shown, in fact, in the next slide I will show it, that the portfolio pi is such that it does not contain any diffusion term, and because it does not contain any diffusion term, therefore, it is riskless. You see, where was the risk coming from? Now, that is the interesting part. Where was the risk coming from? If you look at this, the risk was coming from this. This is non-stochastic, this is non-stochastic, this is non-stochastic. The only factor which is stochastic, which is random, which is unpredictable, is dw. So, the risk is coming from this quantity. So, if there is a portfolio, if I can construct a portfolio in which this dw goes away, the diffusion term goes this is called the diffusion term, this entire thing. So, if the diffusion term goes away, then I have been able to construct a risk free portfolio. So, because this portfolio is risk free, which I will establish just now, because this portfolio, it will generate risk free return over this small period of time, and that gives me that 1 upon t and d pi upon pi, d pi upon pi is the percentage change in price, 1 upon t is the normalization with respect to time. So, per unit time is equal to r. So, if you simplify this, I get dt is equal to r pi dt. Now I establish that this portfolio is risk free. We have shown that d pi is equal to this, we have just shown that because d pi consists of the d pi consists of what? D pi consists of d pi is equal to dc minus delta c by delta s into ds. So, that is precisely what we have put here. dc is this expression from Ito's lemma, dc is this expression from Ito's lemma, minus delta c by delta s is as it is this expression, into ds, and this is ds. Now, if you look at this, look at the coefficients of dw. The coefficient of dw is sigma s dc upon ds minus, there is a minus sign here, this is the minus sign, dc by ds into sigma s dw. So, these two terms cancel out. The very fact that these two terms cancel out means that my d pi, my portfolio, does not contain any stochastic term, does not contain any random term, and because it does not contain any random term, it, in terms of our definition of risk, is riskless, and because it is riskless, it will generate the risk free rate of return. We will continue from here the next.